In a marble quarry, the excavator plays a crucial role in the efficient and professional cutting of stone blocks. This heavy machinery, operated by skilled professionals, employs advanced techniques to ensure precise and rapid extraction. The process begins with the excavator positioning itself strategically near the desired marble vein. Equipped with specialized cutting attachments, such as diamond wire saws or hydraulic hammers, the excavator makes clean, controlled cuts into the marble. Precision is key, as the quality and size of the extracted blocks depend on accurate cutting. The operator carefully maneuvers the excavator to create deep incisions along predefined lines, ensuring minimal wastage and optimal block size. Once the initial cuts are made, the excavator uses its powerful hydraulic arms to apply force, gradually detaching the marble block from the quarry bed. This process, known as block turnover, requires both strength and finesse to avoid damaging the marble. The excavator's agility allows it to adjust its position and angle effortlessly, enhancing the precision of the cut and the safety of the operation. Advanced features, such as GPS and laser-guided systems, further aid in achieving exact cuts and maintaining consistent quality. The professional handling of the excavator not only speeds up the extraction process, but also reduces the risk of accidents and injuries. Operators are trained to navigate the complex terrain of the quarry, ensuring that each block is extracted with minimal disruption to the surrounding material. The result is a high yield of marketable marble blocks, ready for further processing and finishing. The efficiency of the excavator, combined with the expertise of the operator, transforms the challenging task of stone cutting into a streamlined, productive operation, highlighting the symbiosis between technology and skill in modern quarrying. Casting, cutting, and polishing a large ship propeller is a complex and precise process. It begins with creating a detailed mold based on the propeller's design specifications. Molten metal, typically a high-strength alloy, is poured into this mold to form the propeller. Once the metal cools and solidifies, the propeller is removed from the mold and undergoes initial rough cutting to remove excess material and achieve the basic shape. Skilled technicians then perform precision cutting to refine the blade profiles and ensure optimal hydrodynamic efficiency. The final step is polishing, where the propeller is meticulously smoothed and finished using abrasive materials to achieve a flawless surface. This not only enhances the propeller's aesthetic appeal, but also reduces friction, improving the ship's performance and fuel efficiency. The entire process demands a high level of expertise and attention to detail to produce a propeller capable of withstanding the harsh marine environment. Meeting API 1104 standards for welding, especially in pipeline and related facilities, requires strict adherence to technical and procedural guidelines. The process starts with developing and qualifying specific weld procedures that conform to API 1104 requirements. This includes documenting and approving each weld procedure specification, WPS, procedure qualification record, PQR, and welder qualification test, WQT. Weld procedure specification, WPS. The WPS details the parameters for welding, including materials, filler materials, joint design, welding position, preheat and interpass temperatures, and post-weld heat treatment if necessary. These parameters must comply with API 1104 to ensure consistent weld quality and mechanical properties. Procedure Qualification Record, PQR. The PQR records test results verifying that the WPS can produce welds meeting mechanical property requirements. It involves performing weld tests under WPS conditions and subjecting the welds to destructive testing, such as tensile, bend, and hardness tests, to confirm their integrity and compliance with API 1104 standards. Welder Qualification Test, WQT. Welders must be qualified to perform welding according to the WPS. The WQT ensures welders can produce sound welds using the specified procedures. This typically involves welding test coupons evaluated through non-destructive testing, NDT methods, such as radiographic or ultrasonic testing, and sometimes destructive testing. Welding process. 1. Preparation. Before welding begins, the base materials must be thoroughly cleaned to remove any contaminants such as oil, grease, or oxide layers. Joint preparation involves precise cutting, beveling, and alignment to ensure a proper fit-up. 2. Preheating. Depending on the material and thickness, preheating may be required to avoid rapid cooling, which can lead to cracking. Preheating temperatures and methods are specified in the WPS. 3. Welding. During welding, strict control over parameters such as current, voltage, travel speed, and heat input is maintained. Common welding processes used include shielded metal arc welding, SMAW, gas metal arc welding, GMAW, and submerged arc welding, SAA, each selected based on the specific application and material requirements. 4. Interpass temperature control. Maintaining the correct interpass temperature is crucial to avoid weld defects such as lack of fusion or slag inclusions. Continuous monitoring ensures compliance with the WPS. 5. Post-weld heat treatment, PWHT. If required, PWHT is conducted to relieve residual stresses and improve the mechanical properties of the weld. The parameters for PWHT, such as temperature and duration, are carefully controlled. 6. Inspection and testing. Final inspection involves both non-destructive and destructive testing to verify the quality of the welds. Radiographic testing, RT. Ultrasonic testing, UT. Magnetic particle testing, MT. And dye penetrant testing, PT, are commonly used to detect surface and subsurface defects. 7. Documentation. Comprehensive records of the welding process, including WPS, PQR, WQT, and inspection results, are maintained to ensure traceability and compliance with API 1104 standards. By adhering to these detailed procedures and maintaining stringent quality control throughout the welding process, compliance with API 1104 standards is achieved, ensuring the safety, reliability, and longevity of the welded structures.
In a paradigm-shifting fusion of military prowess and logistical ingenuity, a new generation of military vehicles has emerged, ingeniously designed to metamorphose into mobile ferries, specifically tailored for the transport of heavy tanks. These amphibious behemoths represent a cutting-edge solution to the challenges of strategic mobility, seamlessly transitioning from formidable ground vehicles to watercraft with unparalleled efficiency. Engineered with reinforced hulls, advanced water jet propulsion systems, and specialized buoyancy control mechanisms, these multifunctional marvels facilitate the seamless traversal of rivers, lakes, and water obstacles, ensuring the swift and secure transportation of heavy armored units. The transformative capabilities of these military ferries redefine traditional notions of battlefield logistics, offering commanders unprecedented flexibility in deploying tank divisions across diverse terrains. This innovative adaptation not only addresses the complex demands of modern warfare, but also exemplifies a symbiosis of military might and technological advancement. As these adaptable vehicles navigate both land and water with equal prowess, they embody a strategic leap forward, enhancing the military's ability to project power swiftly and effectively in the ever-evolving theater of global conflict. In a remarkable fusion of military ruggedness and agricultural functionality, a military truck has undergone a transformative adaptation, now equipped with a specialized plowing unit designed for farming applications. This versatile vehicle, originally engineered for challenging terrains and tactical operations, seamlessly transitions into a powerful agricultural asset. The integration of a purpose-built plowing unit enhances the truck's utility, allowing it to efficiently cultivate fields with precision. The combination of military-grade durability and farming efficiency reflects an innovative repurposing of technology, demonstrating how adaptable military assets can contribute to civilian pursuits. This dual-purpose military truck, now a vital tool in the agricultural landscape, exemplifies the potential for cross-industry collaborations to address evolving society. Braemar Transformation, a strategic initiative by Fred Olsen Ocean, stands as a pioneering venture within the maritime industry, marked by its profound impact on vessel efficiency and sustainability. This transformative project addresses the imperative of retrofitting existing vessels with cutting-edge technologies to align with contemporary environmental standards and operational demands. With the focus on enhancing performance and reducing carbon footprint, Braemar Transformation integrates advanced propulsion systems, energy-efficient solutions, and digital technologies. Fred Olsen's commitment to sustainability is evident in the meticulous execution of this initiative, where vessel modifications are tailored to specific operational profiles, ensuring optimal performance across diverse maritime conditions. The integration of predictive maintenance algorithms and smart monitoring systems augments operational reliability while minimizing downtime. Through Braemar Transformation, Fred Olsen not only underscores its commitment to environmental responsibility but also sets a new industry benchmark for retrofitting projects, fostering a paradigm shift toward greener and more technologically advanced maritime operations. This initiative not only redefines the operational parameters of existing vessels, but also exemplifies the maritime industry's proactive stance in adapting to the evolving landscape of regulatory standards and societal expectations for sustainable shipping practices. In essence, Braemar Transformation is a testament to Fred Olsen's vision and leadership in advancing the maritime sector towards a more sustainable and technologically sophisticated future. In an unfortunate operational incident, a working bulldozer, a formidable piece of heavy equipment designed for earth-moving tasks, has encountered a setback by inadvertently veering into a 35-foot abyss. The unexpected trajectory into this depression, likely due to operational misjudgment or unforeseen circumstances, has placed the bulldozer in a precarious position. The machine's robust construction and safety features now face a critical test as it grapples with the challenges posed by the abrupt descent. Recovery operations will demand a strategic approach, leveraging auxiliary equipment, such as winches or cranes, to extricate the bulldozer from the abyss without compromising its structural integrity. This incident underscores the importance of vigilant operational practices and the need for contingency planning, emphasizing the intricate balance between the power and adaptability of heavy machinery and the dynamic nature of on-site challenges. In the systematic handling of scrap cars, an efficient approach involves employing an excavator to strategically drop heavy objects for collection and compaction. The excavator, equipped with precision controls, maneuvers into position to deliver targeted impacts on specific points of the scrap car. This controlled force application not only expedites the dismantling process, but also enhances safety and operational efficiency. The heavy objects utilized for impact are carefully selected to optimize the compaction and extraction of valuable recyclable materials from the scrap cars. This method, utilizing the excavator's mechanical prowess, streamlines the workflow in scrap car processing, emphasizing resource recovery and waste reduction within the framework of sustainable and environmentally conscious practices. The meticulous task of changing a 4-ton tire on one of the world's largest trucks within a gold mine involves a team of seasoned experts employing specialized techniques and equipment. Skilled technicians, well-versed in heavy machinery operations, initiate the process with the precise positioning of the massive truck using hydraulic jacks to ensure stability. The confined and rugged environment of the gold mine requires a heightened level of expertise, with safety protocols paramount. Employing advanced tire handling equipment, technicians delicately remove the colossal tire, incorporating torque multipliers and powerful impact tools for precision. The replacement tire, selected for durability in the demanding mining conditions, is meticulously secured onto the enormous wheel hub. This sophisticated operation highlights the fusion of technical acumen, industrial machinery, and safety measures essential for seamlessly changing the 4-ton tire, thereby sustaining the uninterrupted productivity of the colossal trucks vital to gold extraction operations. The World War I tank from 1917 stands as an exemplar of early armored warfare technology, boasting distinctive features that marked a paradigm shift in military tactics. This tank, often typified by the likes of the British Mark I, features a rhomboid-shaped hull constructed from riveted steel plates, providing formidable protection against small arms fire of the period. Equipped with caterpillar tracks for traversing challenging terrains, the tank's mobility was a groundbreaking innovation. The armament consisted of sponsons on either side, housing artillery pieces or machine guns, enabling a broad field of fire. The tank's tracks were independently powered, allowing for varied steering capabilities. The crew compartment, cramped yet pivotal, housed a crew of several individuals responsible for navigating, operating weaponry, and managing the rudimentary engine. The tank's operational range was inherently limited by the nascent internal combustion engine technology of the time, often requiring meticulous maintenance in the field. Visibility was a constant challenge, addressed through narrow vision slits and rudimentary periscopes. While lacking the sophistication of modern armored vehicles, the World War I tank's features represented a groundbreaking departure from conventional military hardware, heralding the advent of mechanized warfare that would shape the course of military history. The production of a saddle-shaped panel is a highly intricate and specialized manufacturing process, integral to industries such as aerospace, automotive, and marine, where complex curved panels are fundamental to structural and aerodynamic requirements. This sophisticated procedure commences with the meticulous selection of advanced materials, typically lightweight alloys or composite materials, chosen for their exceptional strength-to-weight ratios and durability. These materials undergo rigorous inspection and preparation to meet exacting quality standards before integration into the manufacturing line. The shaping of the saddle panel is a multifaceted and precision-driven operation, initiated by a meticulously crafted computer-aided design model that delineates the exact geometry and specifications of the final product. This CAD model serves as the blueprint for the entire manufacturing sequence, ensuring unparalleled accuracy and consistency throughout each stage of production. Once the design is finalized, a specialized forming tool is engineered to replicate the intended shape of the saddle panel. This forming tool is a critical element in the process, demanding a deep understanding of material behavior, stress distribution, and the precise curvature required for the final product. The selected material, having undergone meticulous preparation, enters the forming process, where it is subjected to controlled pressure and temperature within the specialized forming tool. This process, commonly known as metal forming or thermoforming, induces plastic deformation in the material, allowing it to adopt the intricate saddle shape dictated by the tool. The precision in controlling temperature, pressure, and forming speed is paramount to achieving the desired curvature without compromising the material's structural integrity. Modern manufacturing facilities deploy hydraulic or mechanical presses equipped with programmable logic controllers to ensure repeatability and precision in the forming process. In instances where composite materials are employed, the saddle shape panel production may encompass additional steps such as layering and curing. Layers of composite materials, often in the form of woven fibers impregnated with resin, are meticulously arranged to reinforce the structural integrity of the panel. The composite stack is then subjected to heat and pressure in a process known as autoclaving, facilitating the curing of the resin and resulting in a robust, high-strength composite panel. This method offers the distinct advantage of combining lightweight properties with exceptional strength, making it particularly desirable in industries where weight optimization is critical. Post-forming, the saddle shape panel proceeds through a series of secondary processes to refine its surface finish, dimensions, and overall structural integrity. Trimming and machining operations are executed with precision tools, guided by the initial CAD model, to achieve the exact specifications required for the final product. This step is crucial for maintaining tight tolerances and ensuring seamless compatibility with other components in the assembly. Surface treatment and finishing processes follow, enhancing the aesthetic appeal and corrosion resistance of the saddle shape panel. Depending on the material used, these treatments may include anodizing for aluminum panels or painting for composite structures. Quality control measures, such as non-destructive testing and dimensional inspections, are implemented at various stages of production to identify and rectify any deviations from the specified standards. The production of a saddle-shaped panel culminates in rigorous testing procedures to validate its structural integrity, dimensional accuracy, and overall performance. This may involve fatigue testing, stress analysis, and other assessments to ensure that the panel meets or exceeds the stringent requirements for its intended application. The comprehensive nature of this production process, characterized by precision engineering and stringent quality control measures, underscores the intricate interplay of technology and expertise required to manufacture complex and high-performance components in today's advanced industries. The saddle-shaped panel, emerging from this intricate production journey, represents a pinnacle of modern manufacturing, where cutting-edge materials, precision engineering,
Building a JetBoat Kitset by Thomas Hewitt from New Zealand is an exhilarating endeavor that promises endless outdoor adventures. Hewitt's Kitset boats are renowned for their lightweight construction, weighing in at a mere 150 kilograms, making them easily transportable and maneuverable in various water conditions. Powered by the reliable Yamaha Superjet engine, boasting 73 horsepower, these boats may not be the most potent in terms of raw horsepower, but they deliver an incredibly fun and agile experience on the water. Assembling one of Hewitt's Kitset jet boats is not just a project, it's an immersive do-it-yourself adventure. From meticulously piecing together the aluminum alloy hull to fitting the Yamaha engine with precision, each step of the build process offers a sense of accomplishment and excitement. Whether you're a seasoned DIY enthusiast or a novice builder, Hewitt's Kitset boats provide a rewarding challenge and a chance to create something truly special. Creating a JetBoat kitset involves a detailed step-by-step process that encompasses preparing materials, machining components, and assembling them into a fully functional watercraft. This comprehensive guide will outline each stage of the manufacturing process, from selecting materials to testing the finished product, ensuring a thorough understanding of the intricacies involved in building a JetBoat kitset. 1. Materials selection and preparation. The first step in creating a JetBoat kitset is selecting high-quality materials that offer a balance of strength, durability, and weight. Common materials used in JetBoat construction include aluminum alloys for the hull and stainless steel for hardware and fasteners. Aluminum alloys. Choose marine-grade aluminum alloys known for their corrosion resistance and structural integrity. Ensure the material is lightweight yet robust enough to withstand the rigors of marine environments. Stainless steel. Select high-grade stainless steel for hardware such as bolts, nuts, screws, and brackets. Stainless steel offers excellent corrosion resistance, essential for prolonged exposure to water. Once materials are selected, they must be prepared for machining and fabrication. This involves cutting aluminum sheets into precise dimensions for hull panels, as well as machining stainless steel components to fit specific design requirements. 2. Machining components. Machining components for the JetBoat kitset involves several critical processes to ensure accuracy and compatibility with the assembly process. These processes include cutting. Use CNC computer numerical control cutting machines to accurately cut aluminum sheets into the required dimensions for hull panels. Precision cutting ensures tight tolerances and proper fitment during assembly. Bending. Utilize hydraulic press brakes or roll-forming machines to bend aluminum sheets into the desired shapes for hull panels. Precision bending is essential to achieve the aerodynamic contours necessary for efficient hydrodynamic performance. Machining. Employ CNC machining centers to fabricate stainless steel components, such as engine mounting brackets, jet drive housings, and hardware. CNC machining ensures precise tolerances and repeatability, critical for component compatibility and functionality. Throughout the machining process, strict quality control measures must be implemented to verify dimensional accuracy, surface finish, and material integrity. This may involve the use of inspection gauges, surface profilometers, and material testing equipment to validate machining specifications and detect any defects or deviations. Three. Assembly process. With materials prepared and components machined, the assembly process for the JetBoat kitset can commence. This involves carefully following assembly instructions provided with the kit, as well as adhering to industry standards and best practices for marine vessel construction. The assembly process typically includes the following steps. Hull assembly. Begin by assembling the hull of the JetBoat using pre-cut aluminum panels. Join the panels together using rivets, welding, or adhesive bonding, depending on the kit's specifications. Ensure proper alignment and structural integrity to withstand hydrodynamic forces and operational stresses. Propulsion system installation. Mount the Yamaha Super Jet engine onto the transom of the hull using engine mounting brackets. Ensure the engine is securely attached and properly aligned with the jet drive unit for optimal performance. Install the jet drive unit according to manufacturer instructions, ensuring precise alignment and integration with the engine and hull. Electrical and plumbing installation. Install electrical components such as wiring harnesses, navigation lights, instrumentation, and battery systems. Route wiring and cables neatly and securely to prevent chafing or interference with moving parts. Install plumbing components such as fuel lines, coolant hoses, and bilge pumps, ensuring proper sealing and connectivity to essential systems. Finishing touches. Complete the assembly process by adding finishing touches such as seating, storage compartments, and exterior trim. Ensure all components are securely fastened and properly aligned for a polished and functional appearance. (4) Testing and quality assurance. Once the JetBoat Kitset is fully assembled, it must undergo rigorous testing and quality assurance procedures to ensure performance, safety, and compliance with regulatory standards. Testing procedures may include engine testing. Conduct comprehensive testing of the Yamaha Super Jet engine to verify throttle response, power output, and overall performance. Ensure all engine systems, including fuel delivery, ignition, and cooling, are functioning correctly. Systems integration testing. Verify the integration and functionality of electrical and plumbing systems, including navigation lights, instrumentation, bilge pumps, and fuel systems. Conduct tests to ensure proper operation and compliance with safety standards. Sea trials. Perform sea trials in controlled water conditions to evaluate the jet boat's handling, maneuverability, and overall performance. Test acceleration, turning, and stability characteristics to identify any potential issues or areas for improvement. Quality assurance checks. Conduct comprehensive quality assurance checks to verify the integrity of all components, assemblies, and structural elements. Inspect welds, fasteners, and surface finishes for defects or irregularities, addressing any issues promptly to ensure compliance with quality standards. (5) Packaging and shipping. Once testing and quality assurance procedures are complete, the JetBoat Kitset is carefully packaged and prepared for shipping to customers. Utilize durable packaging materials and secure packaging techniques to protect components from damage during transit. Include detailed assembly instructions, diagrams, and support documentation to assist customers with the assembly process. In conclusion, creating a JetBoat Kitset requires meticulous attention to detail, precision machining, and rigorous quality assurance procedures. By following a systematic approach to materials preparation, component machining, assembly, testing, and quality assurance, manufacturers can produce high-quality JetBoat Kitsets that offer exceptional performance, reliability, and enjoyment for boating enthusiasts worldwide.